During this session I'm going to introduce a property of waves which is known as diffraction, or put into other words, the bending of a wave around the edge of an object. Now we see this, or actually we can see this in a couple of examples. For a start, we see it as the bending of water waves around islands, and an example which is often used is if we have a situation where we have water waves and they're passing through a small split, the way that they spread out. Either way, it's an interaction with another object at those boundary areas. So that's what diffraction is. Let's go through some thinking which will build up your understanding of when diffraction occurs and how much diffraction occurs. And there's a number of features that you've got to try and pick out, and they're the important features. So, first of all, imagine I have a barrier with a small gap. So I have a paddle vibrating to produce some waves, and I have a barrier with a very, very small gap. Now, the gap is smaller than the wavelength of the waves, so what's going to happen here? As the waves progress along, all they do is reflect back. Okay, so the wave does not even pass through the barrier because the barrier is too small for the wave to be able to proceed through. So, next situation, similar world, a medium-sized gap. So what do you think will happen if the gap is similar width to the wavelength? In this case, something called diffraction occurs. The waves go forward, and what happens is, having gone through the split, they spread out around the edges. So that's the diffraction process. And actually, when wavelengths are similar to the size of the gap, that's when the most diffraction takes place. If we continue extending this, so we're thinking about a barrier of a large gap now. In this case, as explained, as the waves continue along, we do get some diffraction, but it tends to be quite slight in comparison to the size of the gap just at the end there. So we've got three features, and we can see how the amount of diffraction changes depending on the size of the gap. It's one thing to recognise, and that's a key feature. As well as that, diffraction depends on the size of the obstacle. So, if we've got a situation where we've got quite small wavelengths compared to the size of the obstacle, and wavelengths which are similar to the size of the obstacle. And as we can see, there's less diffraction occurring. The waves aren't bending around the object when the wavelength is very, very small, and if the wavelength is longer, then there will be greater diffraction around an object. That actually works not just with general waves. It can also be thought about if we imagine a house in a valley. What the house in a valley might find is that they're not able to pick up radio or television broadcasts which are at a very, very short wavelength. And this is because the diffraction isn't great enough for the emissions to reach the house. But for longer wavelength broadcasting, because there's more diffraction, then they'll be able to receive those signals and be able to pick up either TV or radio at those longer wavelengths. So both of those points emphasize the fact that at a longer wavelength and a low frequency, there will be a greater amount of diffraction. Huygen's principle is a useful way to imagine this taking place. Remember, Huygen's principle thinks about at every single point on a wave front to be a little wavelet which is producing circular waves going out in all directions. Now, this idea gets us to think about if we're going through a small gap, then the circular waves tend to spread out in all directions, producing an almost circular pattern coming out again. And with a large gap, what we find is that only at the edges does that circular wavelet have any impact, so therefore it appears that the amount of diffraction taking place is much less. So with all those things in place, let's just go over those keynotes again. Longer wavelength and lower frequency means more diffraction. The larger the gap, the less the diffraction. And if the gap is smaller than the wavelength, then no diffraction but reflection. And remember, that optimum level means if the wavelength is similar size to the gap, that means we have the most diffraction taking place. A couple of questions for you. What size must the gap in a barrier be to get the greatest diffraction? Think about it. About the same size as the wavelength of the wave. Why is light not diffracted by a doorway but sound is? Light has much shorter wavelength than sound, so although there's some diffraction, it is unobservable. Okay, so therefore the shorter wavelength means that it's just not observable. So those are the ideas behind diffraction.